It's a pleasure for me to present you our speaker today, who is Polina Feldmann. This will be the first to last seminar in the ESQPT 2021 series. There will be another one next week, and that will be the last. The last one, Polina has studied physics in Marburg and Jena in Germany, and he has just finished her PhD in Hanover, Germany. She had two advisors, Professor Luis Santos from Hanover and Professor Augusto Smerzi from Florence. And now she has just moved to Canada, to Vancouver, where she will continue as a postdoc with Professor under the supervision of Professor Robert Rausendorf. Okay, her main interests are cold atoms, quantum optics, and quantum metrology and information. And today she's going to give, for sure, a very interesting seminar on interferometric order parameters for excited state quantum phase transitions in BECs. That's the same title of a recently published work of that is probably based in her thesis from her group in Hanover. So, Polina, whenever you're ready, we are all yours.
Thank you for the kind introduction, and good morning to everyone from Canada. I have very much enjoyed the previous talks in this seminar series, so I'm very happy that the organizers have invited me to present our recent paper, which is this one. I am going to tell you about an interferometric order parameter for excited state quantum phase transitions in Spino-Bose-Einstein condensates. So our goal is to experimentally distinguish different excited state phases from each other. Imagine that we have a quantum system that depends on some control parameter. And if we look at the energy density spectrum of the system exhibits several excited state phases. We want to find an experimentally accessible order parameter whose value can be used to tell apart neighboring excited state phases. Why do we focus on order parameters? So first, there is this fundamental argument that it is crucial for the concept of phases that we have a qualitative difference between the different phases. And this is captured in a particularly concise way by order parameters. And secondly, when our perspective on this topic is from the point of view of quantum state engineering. Quantum state engineering is the art to design, prepare, maintain, and characterize useful entangled states. Now, it is obviously helpful in designing useful states if we can classify some accessible state by some useful properties, which would be the case if we find a useful order parameter for excited state phase transitions. Furthermore, if we know that some useful property is present throughout an entire phase, this can help us to have a robust preparation of a quantum state with this property. Finally, I would like to remind you that not only the ground state, but all Hamiltonian eigenstates share some crucial property, which makes them a good choice for quantum state engineering. And this is the stationarity under the Hamiltonian evolution. From a broader point of view, quantum state engineering is crucial for many emerging quantum technologies, such as quantum communication and cryptography, or quantum metrology, and of course, quantum simulation and computing. Let me first say again some words about excited state quantum phase transitions, just to emphasize which properties we are going to look on. ESQPTs generalize ground state quantum phase transitions mainly to systems with few collective degrees of freedom, and as we all know, have been introduced by Pavel Zeiner and others in a paper in 2006. Here we see a plot from this very paper which shows the spectrum of an interacting boson model as a function of some control parameter. And we see that an excited state quantum phase transition emerges from a ground state quantum phase transition and cuts the spectrum into two regions. Just as any other phase transition, excited state quantum phase transitions are associated to singularities that appear only in the infinite size limit. This infinite size limit is called, depending on the context, a thermodynamic or mean fit limit. Specifically, the signatures that are most often associated with ESQPTs are similarities in the density of states, in the eigenenergies, in the wave functions, and in various observables. Furthermore, it is known that most ESQPTs correspond to stationary points of the classical Hamiltonian that describes the infinite size limit of the quantum system. And apart from this, also effects on the dynamics and thermodynamics have been observed due to ESQPTs. We will mainly focus on the density of states, on stationary points, and on dynamical properties. Order parameters have been discussed in the literature already, order parameters for ESQPTs. As far as I know, there are three approaches that have been presented so far. The first approach is rather straightforward. It is the idea to take in the excited state expectation value of some observable. This yields an order parameter, for example, for the unrestricted Davis-Cummings model, where one can choose the observable to be just the same, which provides the ground state order parameter. A less obvious approach is idea is to look at the long-term averages of expectation values, as has been presented by Puebla and others in several papers for the Lipkin-Meshkov-Glick and the Dicker model. Here, the idea is that the crucial requirement for the ESQPT is that you have a symmetry breaking that is associated with this excited state quantum phase transition. This symmetry breaking ensures that while in the symmetry preserving phase, all coherences decay in long-time averages of operators. In the symmetry breaking phase, there are coherences that are preserved, and one can tailor an operator and observable such that it probes these coherences so that we can see a clear difference in the long-time average of this observable depending on the excited state phase in which we are. And the third approach that has been presented partly by the same authors for the Rabi and Dicker model and has been also presented to us in this ESQPT series already in the previous talk, is based on sign conserving phase space functions. So if you look at the classical phase space of the main field model that you obtain in the infinite size limit, and then it is often observed that in one of the excited state phases, you have phase space function that preserve the sign along each trajectory within this phase. From this phase space function, it is possible to derive a sign operator such that the expectation of the sign operator will be conserved in the symmetry breaking phase and will not be conserved in the symmetry preserving phase. But altogether, there has been little focus on order parameters so far. Much more attention has been paid to critical properties, which describe the excited state quantum phase transition itself. And also in terms of experiments, there haven't been so many so far on excited state quantum phase transitions. There have been two experimental systems studied in this context. One are molecular spectra, where it has been shown that calculations agree very well with known spectral data. On the right here, we see a monodromy plot with the blue points being calculated and the green triangles being experimental data. And here we see that the monodromy changes from quadratic to linear behavior, which is associated to an excited state quantum phase transitions. In these systems, as far as I know, there has been no discussion of order parameters, and they have the drawback that they offer very limited quantum control. The other platform that has been used so far consists of microwave photonic crystals, which simulate the electronic properties of graphene. Here, a divergent density of states has been observed as a signature of excited state quantum phase transitions. But what I would like to stress is that this is a single particle effect, so that at least entangled states are not involved in this system. and in this observation. Altogether, there is a much larger amount of theoretical papers than of experimental ones, and therefore it was particularly important for us to not only study all the parameters theoretically, but also propose some concrete experiment that is feasible now in nowadays experimental setups. We have chosen spin-1 Bose-Einstein condensates as an experimental platform. Spinobius offer a quantum many-body system that is very well experimentally controlled. They have been already used for the generation of various entanglement states, for example, squeeze states and twin Fock states. Yeah, and even for quantum enhanced metrology, there is a proof of principle demonstration of a quantum enhanced clock in the laboratory of Professor Klempt. Furthermore, they have been also employed for quantum state engineering by adiabatically driving across quantum phase transitions. In this way, an interferometric probe with quantum enhanced sensitivity has been prepared in the U-lab. What has been known about ESQPTs in Spinobius before our work? As I have already mentioned, signatures of ESQPTs have to be studied in the mean field limit. And the mean field model and the mean field dynamics of Spinobius have been well known for a while already, both concerning theory and concerning experiment. Particularly, it has been known that there is a stationary point in the mean field Hamiltonian that corresponds to diverging oscillation periods of the mean field dynamics. And this is a clear sign of excited state quantum phase transitions. Furthermore, as I have already said, Spinobius offer excellent experimental control, which has been particularly nicely shown in the context of mean field theory in the Oberthaler lab, where they have mapped out the entire phase space for mean field phase space for different control parameter values. Recently, a quantum phase transition in the highest excited state of a Spinobius has been revealed by means of by observing the quench dynamics. So this all points signify how suitable Spinobius are as a platform to study ESQPTs. And this has not been noticed only by us. There has been already another interesting talk in the seminar series, for example, about ESQPTs in spin orbit coupled Bose-Einstein condensates. Let me remind you of what a Bose-Einstein condensate is. Imagine that we have a thermal state of n-free non-interacting identical bosons. Usually, if we look at an individual single particle eigenstate and at the relative occupation of this eigenstate, then in the thermodynamic limit, this occupation will go to 0. However, if we go to sufficiently low temperatures, then the relative occupation of the ground state will stay finite in the thermodynamic limit. This phase transition here is called Bose-Einstein condensation of bosons in the single particle ground state. Let me just close the door. The bosons in Bose-Einstein condensates can have internal degrees of freedom. For 3 internal degrees of freedom, we obtain a spin-1 Bose-Einstein condensate. We assume that the bosons are weakly interacting and that they are condensed into a spin-independent spatial ground state. Then the spin degrees of freedom are described by this Hamiltonian, and at the core of which we have the spin-changing collisions here. Q is the quadratic Zeeman effect, which shifts the relative energy of the side modes with respect to the center mode and can be tuned by a magnetic field or by microwave tracing. C is an interaction strength that depends on the scattering length, the mass of the bosons, and the density of the BC. And importantly, this Hamiltonian conserves 2 quantities. First, the magnetization D, And second, the N-not parity I. We are going to focus on ferromagnetic BECs. That means on BECs with a negative interaction strength and BECs with zero magnetization. Therefore, our Hilbert space is spanned by the Fock states with an equal occupation of the two side modes. A typical experimentally realized example of such a ferromagnetic BEC, spin 1 BEC is a BEC of rhodium-87 atoms in the hyperfine ground state. The spin degrees of freedom of such a BEC can be manipulated by means of collective unitary transformations. These transformations affect each boson in the same way. The single boson generators make up the U3 algebra, and the collective generators belong to the constitute the Schwinger representation of the U3 algebra. This U3 algebra, the collective U3 algebra, contains several SU2 subalgebras, each of which is spanned by the three components of some collective spin of pseudospin operator. There is the collective spin 1 operator, but one can also choose two arbitrary independent bosonic modes A and B and define collective pseudospin 1/2 operators. We will use the pseudospin 1/2 operator, which is called S and is constructed from the central mode A0 and from a symmetric superposition of the two side modes G. Importantly, Sx can be realized implemented by radio frequency coupling. The spin degrees of freedom of a ferromagnetic spin 1 BEC with zero magnetization have three ground state quantum phases, which depend on this control parameter, which is basically the ratio of the quadratic Zeeman effect and the interaction strength. In the twin Fock phase, the ground state is a twin Fock state where the atoms are equally distributed among the two side modes. Then throughout the broken axisymmetry phase, the occupation of the center mode increases until in the polar phase, we have all atoms in the center mode. Therefore, the relative occupation of the center mode constitutes an order parameter of these quantum phase transitions. At the very transitions, the energy gap between the first excited state and the ground state vanishes in the thermodynamic limit. This ground state quantum phase transition can be used to generate entangled states. It has been proposed by Zhang and Wan to start from the polar ground state, slowly change psi across one quantum phase transition, such that one ends up in the entangled ground state at the center of the broken axisymmetry phase. In two previous papers, we have shown that this CBA ground state that is generated in this way can be used for quantum enhanced interferometry and to generate microscopic superposition states. The quantum enhanced sensitivity of the state has been demonstrated in the ULab. Again, we will need the mean field model to study the signatures of excited state quantum phase transitions. If you look at if you want to describe an infinite amount of spin 1 bosons, it is sufficient to consider coherent states. In these coherent states, each boson occupies the same single particle state. For such states, the thermodynamic limit of observables can be basically described by replacing operators through C numbers. This yields a classical Hamiltonian model, which for the ferromagnetic spin 1 BEC with zero average magnetization has this form. This is the form of the classical Hamiltonian, where N0 is the relative center mode occupation and phi is the relative phase between the center mode and the side modes. The equations of motion are the usual Hamiltonian equations. So we expect that the excited state quantum phase transitions in the system correspond to stationary points of this Hamiltonian, this mean field Hamiltonian. Before coming to the signatures of spin 1 BECs, I would like to mention that there's a whole bunch of quantum models that converge in the mean field limit to the same classical Hamiltonian. Let us, for example, have a look at the bosonic two-level pairing models that are described, the class of bosonic two-level pairing models that is described by this Hamiltonian density. Here, S and B are different bosonic modes, and mu can range from J to ranges from J to minus J and can include or exclude mu equal to 0. All these Hamiltonian densities are SON symmetric with different n, such that there is a conserved angular momentum. And for 0 angular momentum, these models yield the same mean field model as the one which we study for the spin 1 Bose-Einstein condensate with 0 magnetization. Examples of such bosonic two-level pairing models include the Lipkin-Eshkov-Glick model, vibron models for molecules, or also the interacting boson model for nuclei. And remarkably, with an opposite sign here, interaction sign, this class of bosonic two-level pairing models has been extensively studied. ESQPTs in these models have been extensively studied in a paper by Caprio, Cenar, and Iacchello in 2008, which is a central paper about excited state, central and early paper about excited state quantum phase transitions. So our results complement the results presented in this paper. Let me now come to the signatures. First of all, we look at the spectrum of the spin degrees of freedom of a ferromagnetic spin 1 BEC with 0 magnetization as a function of our control parameter, which, let me remind you, is basically the quadratic Zeeman effect over interaction strength. The critical energy density that corresponds to a saddle point of the mean field Hamiltonian cuts the spectrum into 3 regions. Each of these regions emerges from one of the ground state quantum phases that I have shown to you before. Therefore, we call them the TF prime, the BA prime, and the P prime excited state phases. Along these lines of critical energy density, we see that the individual eigenstates have avoided crossings and thus accumulate there. And this suggests that in the mean field limit, we can expect that the density of states will diverge along these critical lines. And indeed, using the coherent state formalism for the mean field, we can show that the density of states in the mean field limit diverges. Here we show, in this inset, we show cuts through the density of states as a function of the control parameter and of the energy density, and the divergence is clearly visible. This fits very well into a general classification of the singularities in the density of states that are obtained for various kinds of stationary points of mean field Hamiltonians. This classification has been introduced by Stransky and Cenar. The divergent density of state establishes that we really have 3 excited state quantum phases. Now for the remaining 3 slides of signatures, I have always taken one of the order parameters that have been already presented in the literature as a motivation to choose what observable to look on, yes, or which features to look into. In the first approach, as I have told you, the idea is to use an excited state expectation value as an order parameter, right? And the most natural choice to try out is, of course, to use the observable that yields the ground state order parameter, which in our case is the relative occupation of the center mode. Now, if we have a look at the excited state expectation value of this observable, we find that it exhibits singularities at the excited state quantum phase transition. So it is a signature of the ESQPTs, but there is no qualitative distinction of excited state phases. Therefore, it is not an order parameter in our case. The second, what we look at is the classical phase space or mean field phase space and the classical trajectories in this phase space. Here, the red dots indicate the saddle point and the ground state of the mean field Hamiltonian. The yellow curves, for this value of the control parameter, the yellow curves belong to the BA prime phase, and the green curves are the trajectories in the P prime phase. An energy hypersurface subsumes all trajectories that belong to the same energy density. In the TF prime and P prime phases, there's always only one trajectory per energy density. But in the BA prime phase, we have always two trajectories per energy density, one at the front and one at the back of the phase space here. And each of these trajectories breaks the mean field symmetry that arises from the parity conservation in the quantum case, from the not parity conservation. However, we have no associated quantum symmetry breaking, because if we look at the quantum states in the subspace, which is defined by a particular number of bosons, n, and a particular magnetization, d, which is 0 in our case, then n and d fix the parity of n naught. And thus all Hamiltonian eigenstates are eigenstates of the parity operator, and we can have no degeneracy and no symmetry breaking. Therefore, the approach to look at long time averages of observables and the coherences is not viable here. The third approach to order parameters that I have talked about uses phase space functions which preserve the sign in one of the phases and do not preserve the sign in the other of the excited state phases. If you look at this phase space, then clearly we can choose x, the x coordinate to be such a function, because in the BA prime phase, these trajectories are always at positive x or always at negative x, while in the P prime and TF prime phases, the trajectories change the sign of x. If we choose phi1 equal to phi minus 1, this phase space becomes equivalent to the Bloch sphere for the pseudospin operator, pseudospin 1/2 operator S. What does this mean? This means that if we take a coherent, any coherent state, then its x, y, and z coordinates actually on this sphere actually are proportional to the expectation values of Sx, Sy, and Sz with this normalization condition. This means that when we say x is conserved, it's the sign of S, the expectation value of Sx, which is conserved, if and only if the coherent state is in the BA prime phase. Unfortunately, again, the Hamiltonian eigenstates for a fixed n and d, they have a fixed and not parity, right? Therefore, we can conclude that the expectation value of Sx in any Hamiltonian eigenstate will be 0. And this prevents us from defining a sign operator such that the eigenstates would be in some phase eigenstates of the sign operator and some other would not be eigenstates of the sign operator, which is the idea behind this sign operator approach, as far as I understand. Therefore, again, we cannot apply this to our system. Nevertheless, we succeed in defining an order parameter, which is based on the dynamics of coherent states, so came on these classical trajectories. If you look at the trajectories in the TF prime or P prime, or if you look at the trajectories in the P prime phase here, they encircle their knot axis counterclockwise. In the BA prime phase, they do not encircle their knot axis, and in the TF prime phase, which is not shown here because it's for another control, value of control parameter, they encircle their knot axis in clockwise direction. Therefore, this winding number constitutes an order parameter of our excited state quantum phase transitions. From this integral form for this order parameter, one might conclude or expect that the experimental realization will be rather involved. However, luckily, it is possible to rewrite this winding number in a much simpler form. Let tau denote the evolutional period of n naught and not of the entire mean field dynamics, which consists of n naught and phi, right? In the BA prime phase, n naught and phi have the same periodicity. In contrast, in the TF prime and P prime phases, phi of tau equals phi of 0 plus or minus pi. Therefore, we can write the winding number in this very simple and actually experimentally accessible form. This brings me to our proposal for an interferometric measurement of P that gives access to the absolute value of the winding number. Note that P itself is again an order parameter for the excited state quantum phase transitions because it distinguishes the two neighboring excited state phases in our system. Well, first, one has to prepare a coherent state with n naught and phi dictated by the classical trajectory of interest, or which is the same by the point in the phase diagram of interest, and with phi 1 equal to phi minus 1. Then the state is evolved for a time corresponding to one period of the anode dynamics, and it is subjected to an internal state beam splitter. Measuring the expectation value of the relative occupation of the central mode then gives access to P. Here, V plays the role of visibility for this interferometric experiment. The state preparation can be realized by radio frequency coupling and a subsequent microwave phase shift. After the many body dynamics, the beam splitter can again be implemented by a microwave phase shift and a radio frequency beam splitter. Then P is obtained by measuring the occupation of all three internal states. All these ingredients to our experimental scheme have been already demonstrated and used many times in this type of systems. However, it is still not completely obvious that our proposal is experimentally feasible. First of all, to reliably distinguish different values of P, we need a large value of the visibility. The visibility can be maximized by choosing the initial value of a node as close to 1/2 as is possible on the given trajectory. Luckily, for an optimal initial state, we find that the visibility is close to identity almost throughout the entire phase diagram. Then our proposal requires the coherence time of the BEC to exceed one period of the node dynamics. However, we know that this period diverges at excited state quantum phase transitions. Luckily, for a typical interaction strength, the period does not exceed or exceeds a feasible value of 0.3 seconds, only very closely to the excited state quantum phase transition. So 0.3 seconds are indicated by these gray lines here or here, and we see that it cuts out only a tiny little bit of the whole phase diagram. Then, so far, we have always considered exclusively the mean field limit. Experiments, of course, operate with finite size systems. Therefore, we have performed a full quantum calculation to simulate a measurement of P for 100 bosons. And what we see here is that the jump of P that signals the ESQPT is smooth, but luckily P nevertheless clearly distinguishes the different excited state phases from each other. Furthermore, for typical atom number of about 10,000 bosons, the convergence of the mean field limit should be even much better. And finally, magnetic field fluctuations. We have not seen the linear Zeeman effect so far in the Hamiltonian, which I have shown you. We have seen only the quadratic Zeeman effect. This is because I have written everything in a rotating frame that absorbs or hides the linear Zeeman effect due to a constant magnetic field. But now if we add fluctuations on top of this constant magnetic field, this leads to a dephasing of the two side modes against each other. And the strength of this dephasing depends, of course, on the duration of the experiment and on the strength of the amplitude of the fluctuations. This dephasing corrupts our signal by introducing all of these averages of cosine beta here. Therefore, we have to require beta to be much smaller than 2 pi to obtain a meaningful signal. If we assume that we have shot-to-shot noise in a rubidium-87 spin-1 BEC, and the experiment takes 1.3 seconds, this translates into required magnetic field stability far better than at the level of 5 microgauss. Such magnetic field stability has not been demonstrated in this kind of experiments so far, but it seems to be experimentally, technologically feasible. Furthermore, one could increase the density of the BEC to decrease T, the periodicity, and the period of the dynamics, and thus beta. So the requirement would be a bit relaxed. When I arrived at this point, I thought that maybe it makes sense to choose another order parameter which would be less susceptible to magnetic field fluctuations. And let me come back to this slide. So I have thought that this slide shows that we cannot use the sign operator here as an order parameter. This is true, but what we of course can do is we can stop at the part which is shown right now at the slide. So we can, in the order parameter which I have just presented with the winding number, right? We use always coherent states to probe the excited state phase transition. If we confine ourselves to coherent states only, we can of course just use the sign of the expectation value of Sx in coherent states as an order parameter. Then we would get a bifurcation from 0 in one phase to a positive or negative value in the other phase. Unfortunately, so I think this is also a pretty valid order parameter, but unfortunately, it is equally susceptible to magnetic field fluctuations as the one which I have presented. Let me now come to my conclusion. We have established the excited state quantum phase diagram for the spin degrees of freedom of a ferromagnetic spin 1 BC with zero magnetization. And most importantly, we have introduced an order parameter that is based on coherent state dynamics and proposed a feasible interferometric protocol to measure this order parameter. And let me also remind you that the same mean field model, it can be obtained also for different quantum systems. So our results hold also for such systems as like molecules and nuclei. The problems which I am aware of in this concrete project are the sensitivity to magnetic field noise and the subspace artifacts which we encounter. The subspace, what I mean by subspace artifacts is that we want to describe this magnetization zero subspace of the Hilbert, entire Hilbert space, but we describe it in terms of coherent states within the entire Hilbert space. And these coherent states cannot be just confined to a subset of coherent states that spans only the subspace we are interested in. And this leads to this kind of artifacts that we see that there is a symmetry breaking in the mean field limit, but we have no symmetry breaking in the quantum system, that we can probe something only in coherent states, but not in eigenstates. This is not the most elegant thing I can imagine, but I don't know a solution for this problem. And then further prospects related to our paper are that we are eagerly waiting for an experiment or experimental realization of our proposal in the group of Professor Klemmt. Then it would be, of course, interesting to have a look at further order parameters. For example, the quantum Fisher information, which quantifies how useful an entangled state is for quantum metrology. Furthermore, we have realized that the quenches that are typically used to create spin squeezing in Spinobius are actually quenches along excited state quantum phase transitions. And it would be interesting to understand better what the relation between this quench dynamics and the generation of entanglement is, and the excited state quantum phase transition underlying this quench. And then the broader picture, we are interested in applications of ESQPTs for quantum state engineering. And of course, during the following discussion, I would be very happy to hear about further suggestions where you think it would be interesting to, in which direction you think it would be interesting to evolve these results. And before we come to this discussion, I would like to thank my co-authors, Carsten Klemmt, Augustus Merzi, Luis Santos, and Manuel Gessner, and many other people for valuable discussions, particularly Fabian Anders, Dmitro Bondarenko, Pavel Zenna, Ignacio Sirac, Bernd Meyer, and Reinhard Werner. Thank you for your attention. I am looking forward to your questions.
Thank you, Polina. Thank you. Very nice talk. You are very well on time. So we have time for questions and suggestions, as she asked. So if you can raise your hand, and I will moderate the questions. Okay, this is quite a moderated audience, but any question for Polina?
Ami, you have a question?
Armando
Okay.
raised.
First of all, thank you. That was a very, very interesting talk. I want to ask you, if I understand correctly, you are showing here some topological quantum number, what you call the winding number. Now,
Yes.
is that a property of the quantum Hamiltonian, or is that a property of the coherent states that you are using? In other words, does any kind of Hamiltonian with this kind of algebraic structure will have this winding number as a topological quantum number, or are there conditions on the Hamiltonian?
I think that such a winding number can be defined at least in a very large class of Hamiltonians, not only because, so it is mean field based, but here the mean field description is not an approximation, it is a strict limit, right? And therefore, for the entire class of Hamiltonians, which I have mentioned as this interacting two-level bosonic models, we will have such a structure in the strictly defined mean field limit, and thus for these Hamiltonians. In general, I think it has been also observed in many papers on ESQPTs. For example, when Armando Calano says that there are usually phase space functions which conserve the sign, actually this is probably almost equivalent, maybe it is even equivalent to saying there is an access through the phase space which I can define such that some trajectories will go around the axis and some other trajectories will always stay on one side of the axis. Yes, therefore, I think that this is a very general property. That we have winding numbers at all, of course, relies on the fact that our phase space is a sphere, right? And it can be a higher dimensional sphere for systems with more degrees of freedom, and that the trajectories in our models are closed loops, which is true for integrable systems.
So the algebra needs to be compact?
Yes, I think so.
Okay, thank you.
Right, and no, I mean, the fact that we get this compact phase spaces results in principle from particle number conservation, yes. Right? So if we have any model with particle number conservation and we parameterize this, then the particle number conservation gives us a multidimensional sphere as a phase.
So in general, like UN type of models will have this property because of the conservation of the total number.
They will have the property that they have the phase space in the right shape, and then if they are integrable, they will have the property that the trajectories are closed loops. And then I have no proof of this, but I think it is very likely that in many cases, if you have an excited state phase transition, you can define an axis going through the saddle point of the mean field Hamiltonian, which is associated with this transition, such that you will have a winding number that distinguishes trajectories.
Okay, thank you.
Thank you for the interesting
question from Armando. So Armando.
Hi. I don't know if you can see me.
Yes.
Okay. So first of all, thank you for your talk. It was very nice, and I think that these results are quite challenging, so it means that they are very interesting to me. And more than a question, it's just a thought about the problem of this sector artifact, the fact that you have a symmetry which belongs to, which is shared, let's say in this way, by different sectors, and you cannot access it like as measuring, for example, the first component of the angular momentum. I think that another model we have similar properties, the Tavis-Cummings model, which has also, let's say, if you measure the first, you also find that it's equal to 0 in an eigenstate because this operator changed the sector of the Hamiltonian. So the model have similar property. And working with my PhD student Angel, we have found a way to solve this problem, to find a kind of order parameter in the Travis-Cummings model. So maybe it is also possible to make the same kind of trick in your model. So I'm going to think about it, and maybe we can be in touch if I manage to find something. I can write you, and I don't know when I am going to find time to do this, but I think that it's very, very interesting.
And have you published this for the Travis-Cummings model already?
No, it was just a calculation which is in progress and just done because some referee demand us doing something. So we use this Travis-Cummings model, but it's not published. So I'm just seeking time to think about it, and maybe I can write you if I find something which can be interesting.
This would be great. It sounds very useful and interesting because, yes, I know that this problem also occurs in the Travis-Cummings model, but I had not seen any solution in the papers on the Travis-Cummings model so far. Thank you.
I'm muted. Any more questions for our speaker today? I have. Can you show again just the slide where you were showing the expected value of the order parameter, ground state order parameter for excited states?
Yes, sure.
Just a curiosity. This one. Yeah. And so there are in the yellow curve that there were two cuts in your parameter space, isn't it? The yellow and the red.
Exactly. These are the same cuts as shown here. So here I show only the inset. Yes.
And do you have because I think that something very similar happens in the Vibron model that you have these different peaks, one a minimum and a sharp minimum and also a sharp maximum when you cross the two different ESQPTs. Why do you think is this difference that one is a minimum and the other is a maximum? How do you
It's an interesting question. I have to admit that I don't know because I have not thought about this.
Because probably they have different nature, and this is why one is a minimum and the other is a maximum. Maybe for Pavel this is very trivial, but in the Vibron it happens the same, and it's true that the two ESQPTs are different. In that case, this is due to the addition to the Hamiltonian of an harmonic term that lowers.
Yes. So Pavel has been listening to this talk already once because it was in my PhD defense and he was in the committee.
Okay. So
and
he's an expert
there
now.
he actually mentioned, which I did not mention again this time, is that if you look at the spectrum, at the quantum spectrum, yes, it looks as if it were symmetric, right, between positive sign of the control parameter and negative sign of the control parameter. In fact, it is only approximately symmetric, so it becomes symmetric only in the mean field limit. And then this, of course, means that we can expect that these two transitions to show some differences. But it is not at all obvious to me why within the mean field limit we should have this different. Let me think. I mean, we know that, yes, sorry, I'm wrong. I think I know why this is. So if you look at the Hamiltonian and we exchange this, yes, sure. Sorry. If you look at the Hamiltonian and we exchange the sign of psi of the control parameter and simultaneously exchange n naught to 1 minus n naught, yes, then we have a symmetry of the mean field Hamiltonian. I'm sorry.
Okay.
Yes. And this is the same symmetry which gives you a plus and a positive peak in the one station.
Yeah, maximum and a warp, maximum and a minimum. And can you show also the when you the slide where there was the algebraic structure of the model, let's say, when you said that it was a U3 model, but because that was quite fast and I just wanted to because
you mean
the
collective transformations, right?
Yeah, from the beginning, on the onset, I didn't know that there were so many connections with these models, but it is true that they are very, very similar.
So you meant
this
slide,
one,
right?
the one that you were showing, just with the F, the quasi spin and the, because this no, this one. So A and B, these are harmonic.
A and B are arbitrary to independent modes.
Yeah, and these are bosons, just plain
yes.
bosons, I guess. And what then but because for U3 you will need 9 generators and
yes. So SU2 is of course a subalgebra, and SU2 needs 3 generators, and these 3 generators can be chosen such that they are the 3 components of a spin operator.
Yeah, and your SU2 will be the F, that will be the angular momentum for your SU2. It's just that they have the same it's the same structure that it used in the U3 for the vibron model, but in order to build the U3 for the vibron model, you need 3 bosons, and like A and B will be 2 of these bosons, but I was missing the 3rd boson. But
for U3 you of course need 3 bosons, but for SU2 you need only 2.
Yeah, for SU2.
Yes, and here I show only the spins, so the SU2 parts, subalgebras of the entire algebra. The entire algebra is made up from 3 bosons. So here we have A naught for the central mode, A1, and A minus 1 for the 2 side modes. So initially we have 3 modes, and then for practical reasons we look at combinations of 2 modes. And the practical reason is.
Yeah.
Yes,
continue, please.
The practical reason is, first of all, that if we construct the classical model, we find that we have only in the subspace with conserved magnetization, we find that we have only 1 degree of freedom, and the other one goes into a parametrization of the phase space. So we have these 2 parameters in the classical model, which is n naught. This is the relative occupation of the central mode, and phi, which is the relative phase between central mode and side modes, right? But then, in principle, if we want to write down a coherent state, we need a 3rd parameter. And this 3rd parameter is the relative phase between the 2 side modes. But this 3rd parameter does not enter the Hamiltonian dynamics in the mean field limit. Therefore, we can use it just to parameterize the phase space. And therefore, our phase space effectively becomes a block sphere corresponding to a SU2 algebra, subalgebra of the system.
Okay, thank you, Polina. Thank you very much for your explanations, and also for this nice talk. That in particular, I was not aware that there were so many points of contact between this work on BECs and the kind of models of algebraic models I was used to work with. So thank you very much. Is there a last question for Polina? another question, last minute question or comment? If there is not any other questions, so let me thank her. Wish her the best for her stay in Vancouver, and that she enjoys Canada a lot. It seems that it's a very nice city. So I'm sure that you will enjoy it. And tell you that next week we'll go back on Friday, and we will have the last seminar of the series before the summer. So I wish that everybody is safe and all right, and it has been very nice to meeting you as usual. Okay, thank you very much for coming. Bye bye.